At 4:52 p.m. local time in Tokyo today, the floor of the Pacific Ocean slipped. A magnitude 7.4 earthquake tore through a section of the Japan Trench, the same stretch of seafloor that unleashed the 2011 Tōhoku catastrophe. A 10-foot tsunami warning went out for the prefectures of Iwate, Aomori, and Miyagi within minutes. 5 nuclear power plants were placed under emergency inspection, including Fukushima Daiichi itself, the one that melted down 15 years ago. Here is the part almost no one in the mainstream coverage is saying out loud. Today's epicenter sits directly updip of the 2011 slip patch, and fewer than 50 kilometers from where a magnitude 7.3 earthquake struck on March 9, 2011. That earthquake was not recognized as a foreshock in real time. It was only recognized as a foreshock 51 hours later, after the magnitude 9.1 mainshock killed nearly 20,000 people. If this developing story has you hooked like it has me, drop a comment with where you're tuning in from, what time it is there, and whether you think Japan is watching the right fault right now. Because the real question isn't how bad today's earthquake was. The real question is whether the 2011 warning sign just reappeared, and whether anyone will recognize it this time. Let's get into it. At 7:52 and 58 seconds, Coordinated Universal Time, which is 4:52 and 58 seconds in the afternoon in Tokyo, on April 20th, 2026, the seafloor east of northeastern Honshu came apart. The initial magnitude came back at 7.4. Within the first hour, the Japan Meteorological Agency revised its own estimate upward to 7.5. The two numbers sit close enough together that the difference barely matters. What matters is where the rupture happened. 40 degrees north latitude, 142.968 degrees east. Longitude at a depth of 10.9 kilometers. On the subduction interface between the Pacific Plate and the Okhotsk Plate. About 45 kilometers east of the Sanriku coast, and about 100 kilometers northeast of the ruined reactors at Fukushima Daiichi. The Pacific Plate at this location is descending beneath the Okhotsk Plate at roughly 8 to 9 centimeters per year. That is one of the fastest plate convergence rates on Earth. For context, your fingernails grow at about the same rate. Every year, the Pacific Plate pushes another fingernail's length of rock into the subduction zone, and that rock has to go somewhere. Most of it slides smoothly, aseismically, without producing earthquakes, but the interface between the two plates has patches where the rock is locked. Those locked patches are called asperities. They hold the accumulated strain. And when the strain exceeds the friction holding them in place, they break. Today, one of those asperities broke. The shaking reached a maximum observed intensity of 7 on the modified Mercalli scale at Sendai Airport, which is the scientific way of saying very strong. Strong ground motion was reported across Iwate Prefecture, across Aomori Prefecture, across Miyagi Prefecture. In Tokyo, 450 kilometers to the southwest, the Kanto region registered a modified Mercalli intensity of 4. A light shake. Anyone who has ever lived in Japan knows what that feels like. Buildings sway, lamps swing, objects fall off shelves, trains stop, elevators pause between floors. In most parts of the world, this would be the lead story for a week. In Tokyo, on most days, it would barely make the lunch break. Today, it was not the lunch break story. It was the only story. The people watching the tremor roll through the skyscrapers of Shinjuku and Shibuya were not looking at the swaying lamps. They were looking at their phones. They were watching the tsunami warning maps light up for the coast 400 kilometers north of them. And many of them were thinking one specific thought. They were thinking about March 11th, 2011. The Japan Meteorological Agency issued a tsunami warning within approximately 3 minutes of the earthquake's origin time. 3 minutes. That speed is not an accident. That speed is the product of 15 years of institutional learning from what happened the last time this fault moved. The warning was the middle tier of the three-tier Japanese system. Not a tsunami advisory, which is the lowest tier. Not a major tsunami warning, which is the highest. The middle tier. Forecast wave heights were 3 meters for Iwate, 3 meters for Aomori, 1 meter for Miyagi. 3 meters is about 10 feet. 10 feet of water moving at the speed of a commercial jet airliner, because that is how fast tsunamis travel across open ocean. 10 feet is enough to flatten a row of beachfront houses, enough to float cars, enough to drown anyone who did not get to higher ground before the water arrived. Residents along the Sanriku coast were ordered to evacuate. Sirens went off. Train service on the coastal lines suspended. Traffic cameras showed empty highways running inland because everyone who was going to evacuate had already evacuated. Japan moves faster on tsunami evacuations than any country on Earth for a specific reason, and that reason is 20,000 dead 15 years ago. The tsunami itself arrived within roughly 20 to 30 minutes. The largest wave recorded in the first 4 hours measured 1.4 meters at Miyako, about 0.9 meters at Ofinato, about 0.6 meters at Kuji. Those are real tsunami heights. They are not trivial. But they are an order of magnitude smaller than what the Sanriku coast saw in 2011, when run-ups above 30 meters were recorded, and they are an order of magnitude smaller than what the same coast saw in 1896, when a tsunami of 38 meters killed more than 20,000 people. By the 4-hour mark today, the warning had been downgraded to an advisory. By the 6-hour mark, it had been lifted entirely. No tsunami casualties were reported. The system worked. The agency issued the warning inside 3 minutes. The warning propagated. The evacuations happened. The wave came. It came smaller than forecast. And no one died from the water. That is the first piece of good news in this story, and it is worth pausing on, because it will not be the last piece of good news, but it is the first. 5 nuclear facilities were placed under emergency inspection within the first 2 hours. Aftershocks began arriving almost immediately. The magnitude 7.4 today stands as the strongest earthquake on the Japan Trench megathrust since the magnitude 9.1 Tōhoku earthquake of March 11, 2011. That sentence all by itself is why this story is the story, because the Japan Meteorological Agency, in its press briefings today, has not used one specific word. The agency has not used the word foreshock. That is deliberate. And it is the thing the agency has pointedly not ruled out either. Neither has any seismologist I have listened to in the hours since the rupture. The question that lives under every Japanese press briefing this afternoon is whether what just struck was the whole earthquake or whether it was the first one. And to understand why that question is not paranoid, not clickbait, not fringe speculation, you have to understand what happened on March 9th, 2011. On March 9th, 2011, at 2:45 in the afternoon local time, a magnitude 7.3 earthquake struck offshore of Sanriku. Subduction interface. Shallow depth. Tsunami warning. Evacuations. Aftershocks. Let me be specific about the location, because the location is the whole point. The March 9th, 2011 epicenter sits approximately 50 kilometers from where today's earthquake struck. Same fault system, same general neighborhood, same style of faulting. At the time, it made the news, but it did not dominate it. Japan has magnitude 7 earthquakes regularly. A magnitude 7 offshore of Sanriku on the Japan Trench was a serious event that was nonetheless within the normal range of what that fault does. The Japan Meteorological Agency did not use the word foreshock. No Japanese seismologist watching the March 9th rupture unfold in real time said this looks like the precursor to a magnitude 9. The assumption, reasonable at the time, was that the March 9th event was its own thing, a standalone rupture, part of the Japan Trench's ordinary stress release cycle. The aftershock sequence would decay, life would go on. For 51 hours, life did go on. Then, on March 11th, 2011, at 2:46 in the afternoon, local time, the floor of the Pacific tore open for 500 kilometers. The magnitude 9.1 Tōhoku earthquake that followed the March 9th rupture by 51 hours is still, 15 years later, the fourth largest earthquake ever recorded by instruments anywhere on Earth. It is the largest earthquake ever recorded in Japan. It displaced the coast of Honshu horizontally by more than 2 meters. It shortened the length of the day by a measurable fraction of a microsecond by redistributing the planet's mass. It sent a tsunami up the Sanriku coast that exceeded 38 meters in some inlets, a wall of water taller than a 12-story building. That tsunami is what killed 19,759 people. It is what overran the seawall at Fukushima Daiichi. It is what knocked out the backup diesel generators in the basements of the reactor buildings. It is what caused the hydrogen explosions and the triple core meltdown that constituted the worst civil nuclear accident since Chernobyl. And it is what retroactively made the March 9th earthquake a foreshock. The retrospective identification took more than a year. The paper that is now the standard reference on the subject was published in 2012 in the journal Science by Eitaro Kato and Kazushige Obara and their colleagues. What Kato and Obara did was reanalyze the continuous seismic record from the dense Japanese seismic network at a level of detail that was not available in real time to the agency issuing warnings. What they found was striking. The March 9th foreshock was not just a standalone event followed by some ordinary aftershocks. The small earthquakes that followed the March 9th rupture migrated. They did not decay in place, the way aftershocks normally do. They propagated southwest, along the subduction interface, toward a specific location on the fault. That location turned out to be the nucleation point of the magnitude 9.1 rupture that struck 51 hours later. The migration, Kato and Obara argued, was the surface expression of a slow slip event, a quiet, aseismic creep of the fault, a slow unlocking, stress transferring, cell by cell, from the zone that had ruptured on March 9th into the zone that was still locked. And when enough of that locked zone had been pushed past its failure threshold, it failed, all at once, all 500 kilometers of it. The lesson of the Kato and Obara paper is the lesson every seismologist working on subduction zone hazard now lives with. The 2011 foreshock was, in hindsight, detectable. The signal was real. The migration was real. The slow slip was real. And none of it was identified in real time. Not because the Japanese seismic network was inadequate, because it was and is one of the best in the world. Not because the scientists looking at the data were unskilled, because they were among the best in the world. The problem was that no one was looking for the specific pattern Kato and Obara eventually found, because no one had yet seen that pattern produce a magnitude 9. The pattern was only visible in retrospect, after the magnitude 9 had made it visible. The detection problem, in the language of seismology, was not a sensor problem. It was an interpretation problem, and it has not been fully solved. Real-time identification of slow slip precursors is still, 15 years later, not operational in any country on Earth. Which brings us back to today. The magnitude 7.4 that just struck. The epicenter that sits approximately 50 kilometers from the March 9th, 2011 epicenter. The fact that today's rupture sits on the same fault system, in nearly the same neighborhood, with the same style of faulting. Every seismologist in Japan this afternoon is aware of the March 9th analog. Every one of them has, at some level, the Kato and Obara paper in the back of their mind. The Japan Meteorological Agency, in its press conferences today, has not used the word foreshock. That silence is deliberate. The agency's job is to describe what has happened and what the forecast is, not to frighten the public with low probability tail risk speculation. But the agency has not ruled out the foreshock interpretation either. No one has. The reason no one has is simple. It cannot be ruled out. The only instrument that can rule it out is time, and the clock is running. The second clue, the one that elevates today's event from merely concerning to specifically concerning, is not just the distance from the March 9th epicenter. It is the specific location on the fault, not the latitude and longitude in isolation, the position relative to the 2011 rupture patch. And that position is a piece of the story that is getting almost no mainstream coverage at all. When a subduction zone earthquake breaks, it breaks along the interface between the descending plate and the overriding plate. That interface is not vertical. It is tilted, dipping down from the trench on the seafloor toward the hotter, deeper parts of the subduction system beneath the island arc. The shallow end of the interface, the end closest to the trench and closest to the open ocean, is called updip. The deep end, closer to the island arc and the continental interior, is called downdip. Those two words, updip and downdip, are not trivial jargon. They describe a piece of the fault's personality that matters for what kind of earthquake each segment produces, and especially for how big a tsunami each segment produces. Finite fault inversions of the 2011 Tōhoku rupture, including the widely cited paper by Iwate, Baltai, and Barroza, published in Science in 2011, mapped the peak slip region to the shallow updip portion of the megathrust near the Japan Trench axis, offshore of Miyagi and southern Iwate. When researchers cross-reference today's epicenter at 40 degrees north, 142.968 degrees east, against those 2011 slip maps, today's rupture falls at the northern, up-dip edge of the 2011 slip patch. Not beneath it, not far from it, at the up-dip edge, close enough that the stress concentration from the end of the 2011 rupture likely still affects the patch that broke today. Close enough that today's event should be understood as a response to 2011, not as an independent event in a different part of the fault system. Before 2011, the prevailing view among subduction zone seismologists was that the shallow updip portions of the megathrust were weak and aseismic. The idea was that the shallowest parts of the fault were too wet, too unconsolidated, too full of sediments to accumulate the kind of stress necessary to produce a major earthquake. The shallow zone was supposed to slip quietly, creep, deform, release strain without producing a rupture. 2011 demolished that view. The updip zone, it turned out, could rupture, and when it did, it produced the kind of seafloor displacement that killed 20,000 people with water rather than with shaking. The shallow updip region was not aseismic. It was storing strain the same way the downdip region stored strain. It was just storing it in a less obvious way. Since 2011, a substantial body of scientific work has systematically mapped the updip asperities of the Japan Trench. A paper by Takeshi Hirose and colleagues, published in Nature Communications in 2021, used slow slip events recorded offshore in the years after 2011 to identify which patches of the updip interface were still locked and which had relaxed. Hirose and his team identified several still locked asperities in the updip zone, zones that did not slip fully in 2011 and that have been accumulating strain ever since. Today's epicenter sits near one of those mapped asperities. That is not a coincidence. That is the fault system continuing to work its way through the stress field 2011 created. The question is whether today's rupture fully released the strain on that asperity, or whether it released only part of it, leaving an adjacent locked zone that is now carrying an elevated load. This geometry matters for tsunami hazard more than for shaking hazard, and it matters enormously. A rupture in the updip zone displaces the seafloor at the most vertical angle, lifts the most water, and produces the largest tsunami per unit of seismic moment of any location on a subduction interface. If today's rupture had propagated further, if it had migrated from today's patch into an adjacent, still-locked disparity, the tsunami hazard would have increased disproportionately to any increase in magnitude. This is not hypothesis. This is why 2011 was so lethal. The magnitude was catastrophic on its own, but the shallow rupture meant the tsunami was disproportionate to even that catastrophic magnitude. The term seismologists use for events where the tsunami is disproportionate to the magnitude is tsunami earthquake. The term was coined by Aomori in a 1972 paper in the journal Physics of the Earth and Planetary Interiors, specifically to describe events like the 1896 Meiji Sanriku disaster, and we will come back to that one later, because it is the nightmare scenario that still shapes Japanese tsunami doctrine. Today's earthquake was not a tsunami earthquake in the Aomori sense. The shaking at Sendai Airport reached modified Mercalli intensity 7, which is very strong. The earthquake was felt appropriately across hundreds of kilometers. No one was in any doubt that a large earthquake had occurred. The rupture characteristics, as best they can be read from the first few hours of data, look like a conventional subduction interface rupture rather than a slow one. The tsunami that followed was consistent with the magnitude, not disproportionate to it. That is another piece of good news on a day that has had more good news than initial impressions might have suggested. Today was not a tsunami earthquake. It was a conventional subduction earthquake with the tsunami that belongs to its size. But today's location near a still-locked disparity at the updip edge of the 2011 slip patch is the thing that keeps today's event from being fully resolved. Because that asperity is still there. It did not go away when today's rupture ended. 4 months and 9 days before today, on December 11th, 2025, a magnitude 7.6 earthquake struck offshore of Aomori Prefecture, about 200 kilometers north of where today's rupture occurred. That earthquake was on the Japan Trench subduction interface. Same fault system, same style of faulting, same tsunami warning protocol, same reactor inspection protocol. It was handled as a serious event at the time, and then it left the news cycle, the way most earthquakes do, as the world's attention moved on. For the seismologists who watched the Japan Trench, though, the December event did not leave. It stayed in the data. The background rate of small earthquakes in the northern Japan Trench region went up in the months that followed, and it stayed up. The stress field, measurably, had been perturbed. Then, today happened. 4 months later, 200 kilometers south. Same fault system. Another magnitude 7 plus event. And suddenly, what looked in December like a single event looks, with the benefit of one more data point, like the first of a sequence. The working question among Japanese seismologists right now, the question that will define how this story gets told over the next year, is whether December and April are independent events that happened to fall close together in time on a long fault, or whether they are coordinated in a specific sense. Coordinated in the sense that the stress released by the first one elevated the probability of the second, and that the elevated probability is still in play for events that have not happened yet. There are 3 ways this could go. Each one has a different implication for what the rest of the year looks like, and each one has different operational consequences for Japan. The first way is the optimistic interpretation. Under this branch, December and April are releases on a fault segment that is in what seismologists call an extended strain release cycle. In a slow cycle, the accumulated elastic strain on the segment gets discharged in a series of moderate to large events rather than held onto until it can produce a single gigantic one. Under this interpretation, December and April are actually good news. They are the fault doing its job. Every magnitude 7.5 that releases now is energy that is not going to release later in a magnitude 9. Japanese authorities, I suspect, would very much like this interpretation to be correct. It is also, unfortunately, the hardest one to verify in real time. You cannot prove a slow cycle by observing it in progress. You can only prove it by observing the absence of a large event at the end of it, which means, by construction, you need the full cycle to complete quietly before you know that what you were watching was in fact a quiet cycle. The second way is the pessimistic interpretation. Under this branch, December and April are linked, but they are not releasing strain in a way that averts a larger event. They are instead rearranging the stress field in a way that loads a third, still locked patch. In the seismological literature, this pattern is called stress triggering, and the mechanism is straightforward. When one patch of a fault ruptures, the stress that patch was holding has to go somewhere. Some of it dissipates as seismic radiation, which is the shaking you feel. But much of it transfers to adjacent patches of the fault. The patches right next to the ruptured zone experience a step up in the stress acting on them. If those adjacent patches were already close to failure, that stress step can push them over the threshold. Under the stress triggering interpretation, the patches north of December, south of April, or between them could be in exactly that condition. If they are, the next large event on the Japan Trench will not be a third release in a manageable cycle. It will be a stress-triggered rupture of an already loaded asperity, and it could be larger than either of the preceding events. The third way is the most disorienting, because it does not fit either category cleanly. December and April could simply be two unrelated events that happen to strike the same fault 4 months apart, because the Japan Trench produces magnitude 7+ earthquakes at a rate of approximately 1 every 2 to 4 years on average, and the actual occurrence pattern in any given decade is not evenly spaced. It is clustered. You can get 3 magnitude 7s in 1 year and none in the next 5. Under the independence interpretation, today's event has no particular connection to December's event. They are not part of a cascade. They are not linked. They are just 2 earthquakes on a busy fault. The comforting part of this interpretation is that it does not imply anything about what comes next. The uncomfortable part is that it is indistinguishable in real time from the cascade interpretation. The only way to tell them apart is to wait. What seismologists will do over the coming months to try to distinguish between these 3 hypotheses is a combination of stress modeling and monitoring. The stress modeling takes the rupture parameters from today's event and from December's event and computes where, on the rest of the fault system, the static Coulomb stress has been raised. Those zones of raised stress get flagged as elevated hazard zones. The monitoring then watches those zones closely for any sign of unusual seismicity or ground deformation. If the zones go quiet and stay quiet, the cycle interpretation becomes more plausible. If small earthquakes start clustering in those zones, or if ground deformation starts showing up there, the stress-triggering interpretation becomes more plausible. If nothing happens anywhere new for a year, the independence interpretation becomes more plausible. You should expect to hear about the results of this monitoring, piecemeal, over the next 6 to 12 months. It will not produce a clean answer, but it will produce better informed estimates of which of the 3 branches the Japan Trench is on right now. And the monitoring starts today. The aftershock sequence from today's mainshock has already started, and its first days are going to tell us more about which branch of the decision tree we are on than almost any other signal available. There are 2 statistical laws that seismologists use to interpret aftershock sequences, and they are worth understanding in plain language, because you are going to hear both of them invoked in the coming days. The first is called Aomori's law, and it is the oldest empirical law in seismology. It was derived in 1894 by a Japanese seismologist named Fusakichi Aomori, working on the aftershock sequence from the Mino Owari earthquake of 1891. What Aomori noticed was that the rate of aftershocks after a main shock does not stay constant and does not fall off exponentially either. It decays as 1 over t, where t is the time elapsed since the main shock. Double the time since the main shock, halve the aftershock rate. That decay, modified slightly by a Japanese scientist named Tokuji Utsu in 1961, with 2 extra parameters that account for the very early window and the steepness of the falloff, is the baseline expectation for every aftershock sequence on the planet. For Japan, trench subduction zone events, the typical P parameter is close to 1, meaning aftershock rates fall rapidly in the first days and then taper over weeks to months. If today's sequence obeys Aomori's law in the ordinary way, we should see the aftershock rate drop off visibly over the next 1 to 3 days, and then taper out over weeks. The second law is called Bath's law, and it is newer and less reliable. Bath's law is the empirical observation that the largest aftershock in a sequence tends to be about 1.2 magnitude units smaller than the main shock. It is not a physical law. It is a statistical regularity with wide scatter. But it is useful because it sets an expectation. A magnitude 7.4 main shock should, by Bath's law, produce a largest aftershock of about magnitude 6.2. And we have already observed a magnitude 6.2 aftershock today, about 55 minutes after the main shock. That single fact, all by itself, can be read 2 completely different ways. The first way is reassuring. The sequence has already produced its expected largest aftershock. By this reading, we are now past the most dangerous aftershock window, and the sequence is decaying on schedule. The second way is the way I want you to hold alongside the first one, because it is the honest way. Bath's law is a statistical regularity, not a cap. The largest aftershock in a given sequence can be smaller than the Bath prediction, or it can be larger. The scatter is wide. So the observed 6.2 today does not mean a larger event cannot still occur. It means the sequence has now hit the baseline expectation, and from here on, anything larger would be an exceedance. But exceedances happen. Those 2 laws, Aomori and Bath, are what seismologists use to evaluate the ordinary aftershock interpretation. Under the ordinary interpretation, today's earthquake was a main shock. The sequence is already decaying. The largest aftershock has probably already happened, and in a few weeks, we will all have moved on. This is, by base rates alone, the most likely outcome. Most magnitude 7 earthquakes, even on subduction zones with demonstrated capacity for giant earthquakes, are not followed by a larger earthquake. The global base rate is that approximately 5 to 6% of magnitude 7 plus earthquakes are followed by a larger event within 10 days. That number comes from 2 foundational papers, one by Lucille Jones in 1984 in the Bulletin of the Seismological Society of America, and one by Paul Riesenberg in 1999 in the Journal of Geophysical Research. Those numbers have held up through 4 decades of follow-up work. 94 to 95% of the probability mass, in other words, sits on the ordinary interpretation. Today is probably, by default, not a foreshock. But the conditional probability, which is the probability given the specific features of this specific event, is what makes today interesting. The 5 to 6% global base rate is a starting point. It goes up in certain conditions. It goes up when the event is in a subduction zone that has demonstrably produced giant earthquakes, and the Japan Trench has produced the largest earthquake in Japanese history. It goes up when the event is located near the edge of a recently ruptured patch, because stress concentration on the boundary between ruptured and unruptured fault is a known mechanism for triggering the still locked segment. And it goes up when a structurally similar precedent exists, because the precedent demonstrates that this specific fault system, under conditions that resemble the current conditions, has previously produced a foreshock-mainshock pair rather than a standalone event. All 3 of those conditional elevations apply here. that does not flip the probability. It shifts it. The honest range, given all of those conditionals stacked, sits in the 5 to 15% window. Maybe a little higher. That is not a prediction. It is the statistical context you should be holding when you read the next few days of coverage. What the seismologists are actually watching beyond the raw aftershock rate is the aftershock geometry. This is where the Kato and Obara analog becomes operational. If the small earthquakes that follow today's mainshock stay inside the mainshock rupture patch, which is what aftershocks normally do, the signal is reassuring. A decaying swarm of events inside the zone that just broke is ordinary physics. It is the rupture patch settling. But if the small earthquakes start to migrate, if they walk along the subduction interface toward the still locked patches north or south of today's rupture, that is the signature of slow slip. That is the 2011 pattern. That is the thing Kato and Obara identified in retrospect. The Japan Meteorological Agency has, since 2011, been building capacity to watch for this signal in near real time. They will not publicize the monitoring, but it is happening. And if the migration shows up, you will see it in the form of advisories, extended evacuations, restrictions on coastal activity, reactor stand-down orders that extend beyond their original window. Watch what the agency does, not what it says. The actions will tell you what the data is showing, even when the press briefings will not. There is a third thing they are watching, and this one is quieter, but it is critical. They are watching the GPS stations. Japan has an extraordinary geodetic monitoring network called GeoNet, the Global Navigation Satellite System Earth Observation Network, with more than 1,000 continuously operating GPS sites across the archipelago. GeoNet can measure ground motion at the level of millimeters per day. In the lead up to the 2011 earthquake, the Kato and Obara retrospective work showed that ground deformation offshore was changing in ways that, had they been visible in real time, would have been consistent with slow slip on the subduction interface. Today, GeoNet is being read minute by minute by scientists at the Geospatial Information Authority of Japan. If there is ground deformation now, in the hours after today's earthquake, that does not match the pattern you would expect from a simple settling of the rupture patch. That will show up in the GeoNet time series first. The scientists will see it before the agency will announce it. The agency will act on it before the public will hear about it. This is the actual real-time precursor monitoring program that did not exist in 2011 and does exist now. It was built by learning from the worst day in modern Japanese history. The next 72 hours will be the first major test of whether it can do the job it was built to do. And while the scientists are watching the fault interface, the country is watching something else. 5 specific buildings. 5 nuclear facilities went into emergency inspection today. I want to name them in order, because the naming matters. Fukushima Daiichi, the one that melted down in 2011, and that is still in the middle of a decommissioning process that will take decades. Fukushima Daiichi, a few kilometers south of Daiichi, which came perilously close to a similar outcome in 2011, but survived because its backup power stayed up long enough. Onagawa, operated by Tōhoku Electric, which was the closest major nuclear facility to the 2011 epicenter, and which survived the tsunami because of an engineering decision years earlier that set its seawall higher than regulations required. Higashidori, also operated by Tōhoku Electric in Aomori Prefecture, which is currently not generating power and has been in extended shutdown. And Tokai Daiichi in Ibaraki Prefecture, the oldest commercial reactor in Japan, and the subject of litigation about its restart for years. All 5 were placed under inspection. All 5, as of this recording, have reported no abnormalities. That is the second piece of good news in the story. The inspections held. I want to dwell on Fukushima Daiichi for a few minutes, though, because Fukushima Daiichi is not a normal operating nuclear plant. It is a decommissioning site, and it contains an inventory of nuclear material that exists nowhere else on Earth. Inside the ruined reactor buildings, there are approximately 880 tons of melted fuel debris, the solidified remains of the 3 cores that went molten in 2011. That debris sits at the bottom of the reactor pressure vessels, and in some cases has melted through the pressure vessels and into the containment structures below. Removing it is one of the hardest engineering challenges in the history of the nuclear industry. It is being done slowly with robots over decades, and the total timeline for completion is measured not in years, but in generations. In the pools above the reactor cores, there is spent fuel that still needs to be cooled and managed. In the storage tanks around the site, there is more than 1 million tons of processed water with varying levels of tritium that Japan has been slowly releasing into the Pacific Ocean under an internationally agreed plan. All of this was shaken today. The robots, the fuel, the water, the tanks, the piping, the cooling systems, the radiation monitors, shaken but not broken. The site reported no abnormalities. The peak ground acceleration at the Fukushima Daiichi site today is preliminarily estimated at roughly 150 to 200 centimeters per second squared. The design basis for the site, which is the level of ground motion the site's structures are engineered to withstand, is 600 centimeters per second squared. That was updated after 2011, when the actual ground acceleration at the site during the mainshock exceeded the pre-2011 design basis. Today's shaking was well within the revised envelope, roughly a quarter to a third of what the site is now built for. The tsunami at the site today was under 1 meter, well below the reinforced seawall that has been rebuilt since 2011. The site monitoring network, the radiation monitoring network, and the cooling systems are all functioning. Tokyo Electric Power Company issued a statement within the first few hours confirming no abnormalities. Japanese regulatory authorities confirmed it independently. The International Atomic Energy Agency was briefed. As of this recording, Fukushima Daiichi is in the same state it was in yesterday. That is an engineering achievement worth acknowledging openly. The site has been made over 15 years of painstaking work, substantially more robust than it was in 2011. Today demonstrated that. Here is the question that lives under every Japanese nuclear briefing, and especially every briefing about Fukushima Daiichi, and that lived under today's briefings, whether it was asked out loud or not. What happens if today was not the whole earthquake? What happens if the magnitude 7.4 is the March 9th of 2026, and the real event is still ahead of us? The revised design basis at Daiichi would be tested far more severely by a magnitude 8 or 9 rupture in the near field. The seawall, rebuilt to withstand a worst-case tsunami based on 2011, would be tested by a tsunami in the worst-case regime. The fuel debris, the storage tanks, the partially decommissioned reactor buildings would be subjected to shaking and to water loads that are at or beyond what the site is engineered to survive. No one in the Japanese nuclear establishment is saying any of this out loud today, because the scenario is, as I have been trying to emphasize, relatively unlikely. 5 to 15% at the upper bound of reasonable estimates. But it is not zero. And the cost of being wrong, at Daiichi specifically, is a second nuclear accident at the same site, at a site whose inventory of contaminated material is larger now than it was in 2011. This is the unspoken question under today's event. I am going to speak it because it is the honest context, but I am also going to bracket it carefully. I am not telling you that a second Fukushima accident is coming. I am telling you that the system that exists today, to make sure it does not come, which is the monitoring network, the revised design basis, the rebuilt seawall, the Nuclear Regulation Authority's inspection regime, the evacuation plans, the cabinet-level disaster coordination, is being exercised today at a level it has not been exercised since 2011. That exercise is mostly going well. The inspections held, the seawall held, the monitoring held. The good news column is long, but the exercise is not over. The aftershock sequence will run for weeks. The foreshock probability, while small, is not zero, and the institutions that responded today are going to stay on heightened alert for as long as the statistical window is open. You should trust that stance. You should not be reassured by premature all clears, and you should not be alarmed by the mere fact that alerts remain active. The alerts remaining active is the system working as designed. You cannot understand today's event, or the weight with which the Japanese public is receiving it, without understanding the coast it struck. The Sanriku coast runs along northeastern Honshu, from the top of Aomori Prefecture in the north, down through Iwate, and into northern Miyagi. It is what geographers call a Ria coast, which means its shoreline is carved into long, narrow inlets that funnel tsunami energy the way loudspeakers funnel sound. The same wave that arrives at an open coast at 2 meters can arrive at the back of a Sanriku inlet at 20 meters. This geography has, over the recorded history of the coast, produced some of the deadliest tsunamis in human history. In the last 130 years, the Sanriku coast has suffered 3 of them. Each one killed thousands of people. Each one should have been enough to drive the surviving population inland and out of the inlets forever. None of them did. Because the fishing is good, because the towns are old, because the culture is rooted to the places it sits in, and because, between the disasters, the coast is one of the most beautiful places on the islands of Japan. The first of the 3 was the Meiji Sanriku earthquake of June 15, 1896. It is the benchmark for how bad a tsunami can be relative to its earthquake's magnitude. Surface wave magnitude estimates place it at approximately 7.2. The shaking itself was modest. Many coastal residents felt it but did not evacuate because the shake did not seem strong enough to justify the effort. That was a fatal mistake. The tsunami arrived about 35 minutes later, with a run-up of 38.2 meters at the village of Ryori. 22,066 people died. Entire villages were swept out to sea. The mechanism Kanamori proposed in 1972 in his Physics of the Earth and Planetary Interiors paper was that the rupture had been unusually slow. A slow rupture, in physics, radiates less high-frequency seismic energy. Less high-frequency energy means less shake felt at the surface. But the total slip, the total displacement of the seafloor, can still be large. That displaced seafloor still lifts the same amount of water. The tsunami is the same size. The earthquake just feels smaller. That is why tsunami earthquakes are so dangerous. They trick the people on the coast into thinking the threat is smaller than it is. The Meiji Sanriku event is the reason modern Japanese tsunami doctrine trusts the water over the shake. If the water says tsunami, the shake does not get to vote. Every Japanese coastal evacuation drill, every warning siren network, every coastal elementary school's tsunami protocol, every convenience store's escape route signage traces back to the lesson of 1896. Today's 3-minute warning issuance is the operational legacy of that single 19th century catastrophe. If you ever wonder why Japan is so much better at this than the rest of the world, the answer is 1896. The second of the 3 was the Showa Sanriku earthquake of March 3, 1933, 37 years after Meiji Sanriku, on essentially the same coast. This one was different in mechanism. It was a magnitude 8.4 event, but it was not a subduction interface rupture. It was an outer rise normal fault event, which means the rupture was seaward of the trench, in the oceanic plate itself as it flexes on its way down into the subduction zone. Different physics, different part of the fault system, but the tsunami was similar. The run-up reached 28.7 meters at the same village of Ryori that had been devastated 37 years earlier. 3,064 people died. The lower death toll relative to Meiji Sanriku reflected improvements in coastal preparedness over the intervening 3.5 decades. More seawalls, more organized evacuations, more cultural memory of the 1896 disaster, alive in the living elders of the coastal villages. 37 years is within the reach of a human lifetime. People who had lived through Meiji Sanriku as children were grandparents in 1933. That memory saved lives. The third of the three was the 2011 Tōhoku earthquake, 78 years after Showa Sanriku. Magnitude 9.1, run up above 38 meters at Miyagi and approximately 40 meters at other Sanriku locations. 19,759 dead. The largest earthquake in Japanese history. The third of 3 catastrophic tsunamis to hit the same coast in 130 years. And now, 15 years after 2011, another magnitude 7.4 offshore event has struck the same coast. The tsunami today was a fraction of those 3 historical catastrophes, and that is what you should take home as the baseline. Today was not a repeat of 1896 or 1933 or 2011. The wave heights today were 1.5 meters and under. The evacuations worked. Nobody died from the water. But look at those intervals. 37 years between the first 2. 78 years between the second and the third. 15 years between the third and today. If today is the end of the story, that 15-year interval is a comfort. If today is the March 9th of 2026, then 15 years might turn out to be a coincidence rather than a reprieve. And that is what everyone along that coast, right now, is holding in their mind as they decide whether to go home tonight or to stay on high ground for one more day. Within the first hour of today's earthquake, the social media response arrived, and it arrived in the form that all major geophysical events now produce. There were claims that the event was engineered. There were claims that a secret weapons program was responsible. There were claims that oarfish had been spotted on Japanese beaches in the days before. There were claims that a solar flare had triggered the rupture. There were screenshots, decontextualized quotes, pseudo-scientific diagrams, and confident assertions from accounts with no apparent expertise. I am not going to pretend this traffic does not exist, because it does exist, and it shapes how millions of people will understand this event. Instead, I am going to walk through the 4 most common alternative claims, give each one the honest hearing it deserves, and then tell you what the data actually says. This is the part of the video where I do what I always do, which is take the claims that the audience is actually encountering seriously, and then check them against the physics. The first claim is HAARP. The High Frequency Active Auroral Research Program is a real facility. It exists in Gakona, Alaska. It was originally a Department of Defense project, is now operated by the University of Alaska Fairbanks, and its function is basic research on the ionosphere. It consists of a large array of high-frequency transmitters that can beam radio energy upward to heat small volumes of the ionosphere for the purpose of studying how the ionosphere responds. Its rated output is approximately 3.6 megawatts. Claims that HAARP causes earthquakes have circulated online for decades, and they have circulated with particular intensity around every major Japanese earthquake since before 2011. Today's event generated the same traffic, almost word for word. So let us do the math. A magnitude 7.4 earthquake releases approximately 10 to the 15th joules of seismic energy. That is roughly equivalent to 240 kilotons of TNT, or about 12 times the yield of the Hiroshima bomb. HAARP's full rated output, operated continuously for an entire day, delivers approximately 3 times 10 to the 11th joules. The gap between what HAARP can produce in a day and what today's earthquake released is 8 to 9 orders of magnitude. In plainer language, HAARP would have to operate at full power, continuously, for between 100 million and 1 billion days, and have every joule it produced somehow get into the fault at the right depth in order to release the energy of today's earthquake. That is before you even account for the fact that ionospheric radio heating has no known coupling mechanism to rock at 100 kilometers depth. The physics does not support the claim. It does not support it by such a wide margin that no reasonable interpretation of the observed energies can close the gap. HAARP did not cause this earthquake. It cannot cause this earthquake. That has to be said plainly, because the people repeating the claim are not going to say it. The second claim is the directed energy weapon claim. This is a looser family of claims, because it is not tied to a specific facility. It is the assertion that some classified system, whose existence is not publicly acknowledged, has the capacity to trigger earthquakes. The claim is unfalsifiable by construction, because any evidence you produce against it is dismissed as the cover story. I cannot argue against an unfalsifiable claim with data alone. What I can do is tell you what the professional community thinks, and let you draw your own conclusion. In 2016, a survey was published in the journal Environmental Research Letters, led by Christine Shearer and Mick West, along with Ken Caldera and Stephen Davis. The survey asked 77 atmospheric and geophysical scientists from diverse institutional backgrounds whether they had ever encountered evidence in the course of their professional work of large-scale atmospheric or geophysical manipulation programs. 76 of the 77 said no. One said maybe, but described evidence that the other 76 found unpersuasive. That is not a proof of absence. Absence of evidence never is, but it is the honest statement of where the people who would be in a position to encounter such evidence, if it existed, actually are. You can decide for yourself what weight to put on that. I put enough weight on it that I do not believe any of today's earthquake was produced by a directed energy system. I put less weight on it than I would if the same question had a neat physics-based answer, which for this class of claim it does not. The third claim is the one I want to spend more time on, because it is not actually a fringe claim. It is an active, ongoing research topic in peer-reviewed seismology, and there is a real chance it is correct in some restricted form. The claim is that solar and geomagnetic activity can modulate earthquake triggering on already loaded faults. There is a substantial literature on this. A paper by Vito Marchitelli and Paolo Harabaglia and their colleagues, published in Scientific Reports in 2020, analyzed decades of global earthquake data against solar wind speed and reported a statistically significant correlation between high solar wind speed periods and large earthquake frequency. More recently, in February of 2026, a team at Kyoto University led by Mizuno, Kao, and Umeno proposed a capacitive coupling mechanism by which geomagnetic field changes could induce small stresses in the crust that, on a fault already near failure, could in principle tip it into rupture. The proposed mechanism is small. The induced stresses are orders of magnitude smaller than the ambient tectonic stress. But on a fault that is 99.99% of the way to failure, small is all you need. The Kyoto framework is new, unreplicated, and still controversial. It is also not dismissible. If you had asked me 6 months ago whether solar seismic coupling was physically plausible, I would have said probably not. Today, I would say probably not, but we should keep watching. The problem for applying any of this to today's specific earthquake is that the sun, in the 72 hours before today's rupture, was quiet. There was no Earth-directed coronal mass ejection. There was no major flare. The largest flare of the preceding week was a C-class, which is low. The KP index, the standard measure of geomagnetic activity, stayed between 1 and 3, which is calm. Solar wind speed was in the ambient 400 kilometers per second range, which is ordinary. If solar seismic triggering is a real effect, today's earthquake is not an example of it, because the driving conditions were absent. That is not a refutation of the broader framework. It is a constraint. It is a negative data point that the framework has to accommodate, which is how science is supposed to work. Any hypothesis that predicts solar seismic coupling should also predict when coupling will not occur, and today, on the conditions described, coupling should not have occurred. The earthquake happened anyway. Which means, at minimum, today's earthquake was mechanically produced by subduction interface physics, not by external solar forcing. The sun did not do this. The fourth claim is the one that recurs in every Japanese earthquake, and it is the oarfish folklore. The Ryugu no Tsukai, the messenger of the sea god, the giant silver deep water fish that Japanese tradition says surfaces before earthquakes. The folklore is ancient, it is emotionally resonant, and it is falsifiable. A 2019 paper by Yoshiaki Orihara, Masashi Kamogawa, and Toshiyasu Nagao in the Bulletin of the Seismological Society of America did what falsifying a folklore claim requires. They went back through decades of oarfish sighting records, 345 of them, and cross-referenced the sightings with earthquake occurrence. The correlation was not statistically significant. The folklore, in other words, is not supported by the data. This will not stop people from repeating it when oarfish wash up somewhere on the Pacific Rim in the next few days, which they will, because deep sea fish occasionally wash up on coasts for reasons that have nothing to do with earthquakes. The folklore is durable because it is beautiful. The data is clear that it is not predictive. Both of those things can be true at once. Let us talk plainly about what the next few weeks look like under each of the possible outcomes of today's event, because this is the part that actually matters for anyone paying attention. There are three branches of the decision tree. The first and most likely is that today's earthquake was a standalone mainshock. Under this branch, the aftershock sequence will decay through Aomori's law over the next weeks to months. The largest aftershock has probably already occurred, at the magnitude 6.2 we observed today. The sequence will produce smaller events in declining frequency for roughly 3 to 6 months. The tsunami risk has already largely resolved. The nuclear inspections will complete without issue. Life on the Sanriku coast will return to what passes for normal on the Sanriku coast, which is to say, it will never be entirely normal, because nothing on that coast is ever entirely normal. By this time, next year, today's earthquake will be a footnote, an entry in the catalog, another magnitude, 7+ on a fault that has produced many of them. This is the branch the Japanese authorities are quietly hoping for. By base rates, it is the branch they should expect. The second branch is the one that haunts everyone who knows the March 9th, 2011 story. Under this branch, today is a foreshock, a larger earthquake, somewhere between magnitude 7.5 and magnitude 9, follows within days to weeks. Which magnitude exactly depends on which adjacent segment fails and how much it slips. A magnitude 8 is the most plausible escalation, targeting one of the still locked asperities in the updip zone that Hyros and colleagues mapped in 2021. A magnitude 9 is the worst case, requiring multi-segment rupture similar to what happened in 2011. Under the branch where this happens, today's evacuation is not an inconvenience. It is a life-saving rehearsal. The nuclear inspections today are not theater. They are the dry run for inspections that will have to hold a week or two from now in the middle of a worse event. The public messaging today, the cabinet coordination today, the monitoring networks watching the fault interface today are all the first stage of a response that has to hold through a much harder test. The probability of this branch, as I have tried to emphasize, is not large, 5 to 15%, at the upper bound of reasonable estimates. But the consequences, if it happens, are catastrophic. The third branch is the one I want you to sit with, because it is the strangest and the most scientifically novel. Under this branch, today's earthquake is not a standalone mainshock, and it is not a foreshock. It is part of an extended strain release cycle in which the Japan Trench, for reasons that current models do not fully describe, produces a series of moderate to large earthquakes over a period of years, without any single event dominating. The aftershock rate stays elevated for weeks or months, rather than decaying cleanly. Moderate events continue to occur. No single magnitude 9 arrives. Over a period of years, the total seismic moment released approaches what would otherwise have been released by a single gigantic rupture, but it is released in steps. The 2012, 2016, 2021, 2022 events on the Japan Trench, combined with the December 2025 Aomori event and today's event, might already constitute the beginning of such a cycle if this third branch is what is happening. Under this interpretation, today is not the end. It is not the beginning. It is an intermediate step in a process that takes decades to resolve, and that is not well described by current frameworks. This branch would be the most scientifically novel of the three, and it would also be the most operationally uncomfortable, because it would imply that Japan is in an extended heightened hazard regime with no clean end date. The distinction between these three branches will not be resolved today. It will not be resolved this week. It will be resolved piecemeal over the next 6 to 12 months, as the aftershock sequence either decays cleanly or does not, as the GPS data either shows normal post-rupture relaxation or shows anomalies, as additional earthquakes either occur or do not. The quiet work of seismology, which is the work of watching what a fault does over time and updating your model of what it is capable of, is the work that matters from this point forward. The drama is today. The answer is later. Whichever branch turns out to be correct, the ordinary people living on the Sanriku coast have to make their decisions now, tonight, with no access to the answer that will only be available after the fact. I want to close by pulling back from the Japan Trench specifically, because the questions today's event raises are not only Japanese questions. The fault that broke today is one instance of a globally distributed class of fault. Every major subduction zone on Earth, and there are many of them, is capable of producing earthquakes in the magnitude 7 to magnitude 9 range. The Cascadia subduction zone off the Pacific Northwest of North America is capable of a magnitude 9. The Chilean subduction zone in the southern cone of South America has produced multiple magnitude 9s in historical time, including the largest earthquake ever recorded, the magnitude 9.5 Valdivia earthquake of 1960. The Sumatran subduction zone produced a magnitude 9.1 in 2004, a tsunami that killed more than 200,000 people across the Indian Ocean. The Alaskan subduction zone produced a magnitude 9.2 in 1964. Each of these fault systems is sitting somewhere in its own strain accumulation cycle, in its own relationship between locked and creeping segments, in its own statistical regime of foreshocks and mainshocks and aftershocks. What today teaches us, or more precisely, what today reminds us of, is that the science of distinguishing foreshock from mainshock in real time is still not solved. 15 years after 2011, with the best monitoring networks humanity has ever built, with the Cato and Obara paper sitting in every seismologist's filing cabinet, with billions of dollars of GeoNet infrastructure and real-time seismic processing and cabinet-level coordination, we still cannot look at a magnitude 7.4 on a subduction interface and tell you, with confidence, whether it is the end of a story or the middle of one. The reason this matters for the rest of the world is that the same uncertainty will greet every future magnitude, 7 in every future subduction zone, until or unless the science improves. Cascadia, when it eventually produces its next rupture, will be subject to the same ambiguity, and the populations of Vancouver and Seattle and Portland will be making the same agonizing choices about whether to evacuate or stay, whether to trust the first event or prepare for a worse one. Chile, Peru, Indonesia, the Philippines, Mexico, Alaska, every coast that sits on top of a subduction zone will eventually face a moment like today's. Each of those moments will be a test of the monitoring infrastructure, the public messaging, the political will, and the scientific interpretation that the relevant society has built. Japan, today, is running that test in real time, with the full weight of its 2011 memory pressing down on every decision. The test is going well so far. The test is not over. There is one more thing worth saying before we close. The 2011 foreshock was not recognized because no one was looking for its specific signature. The Kato and Obara paper, the one that retrospectively identified the slow slip migration, was published after 2011, and it taught seismologists what to look for in future sequences. 15 years of monitoring work have gone into building the capacity to detect that signature in real time. Today, somewhere in a seismology laboratory in Tokyo or Sendai or Tsukuba, that monitoring capacity is being exercised. Scientists are watching the aftershock locations migrate, or not migrate. They are watching the GPS time series deflect, or not deflect. They are watching the fault interface for the first hint of anomalous motion. If they see something, the public will not hear about it first. The agency will hear about it first, and the agency will act, and we will see the actions before we see the announcements. Watch the actions. Watch the advisories, the extended evacuations, the reactor stand-downs, the tsunami warning reissues. If those actions intensify rather than relax, that is the signal. If they relax on schedule, that is also the signal. The machinery that did not exist in 2011 exists now, and it is running. For the first time since that catastrophe, we are about to find out whether it can do what it was built to do. So here is where I want to leave you. The real question isn't how bad today's earthquake was. The real question isn't even how bad it will get. The real question is whether the 2011 warning sign just reappeared in a form recognizable enough, this time that the people trained to see it can actually see it while there is still time. Because if it did, and if they can, then today's evacuation, today's inspection, today's briefings, today's watchfulness are the first stage of a response that saves lives. And if it did not, or if the signal is too subtle to separate from the noise, then today is simply a loud earthquake that ended cleanly, and we walk away from this story with a reminder of how much there is still to learn. Either way, the fault is watching us. And for the first time in 15 years, we are watching it back, with the tools we built specifically because of what it did to us last time. Whether those tools work, and whether we recognize the warning, if it is in fact there to be recognized, is the question that will define the next few weeks. The clock is running. The sensors are listening. And the Sanriku coast, the coast that has now been on the losing end of 3 of the deadliest tsunamis in human history in just 130 years, is waiting to find out which branch of the decision tree it is on. The rest of us should be watching with them,